This talk will be about a system, NetBouncer, that has been deployed in Azure for 3 years and has detected many failures ignored by previous monitoring systems. Here's a motivating example of Anna's. Anna works in a big data center company as a network operator. One day, Anna got complaints from multiple customers complaining that they've experienced unstable network services. Now Anna had to go and examine the network. And here's a simplified data center network topology, where the circles are the servers and the squares represent the switches and routers. The problem Anna could observe is that sometimes the package sent from the customer server cannot reach their destination, in this case, a storage server. The question is where the packets were dropped. Anna assumed that she could find some faulty switch or faulty link along the way between these two servers by using some traditional monitoring system, which will collect the statistic information from all the switches using protocols like SNMP. But unfortunately, this was not the case this time. The monitoring system told Anna that everything was fine. But of course, the package kept losing, and our customers kept complaining. So Anna had to manually log into the switches and using ping or traceroute or other troubleshooting tools to explore what was going on. However, because there are multiple equal cost paths between these two servers, it is unclear to Anna where the problem is. And Anna had to explore a relatively large network region based on her own troubleshooting experiences and intuitions. This process is tedious, error-prone, and more importantly, is time-consuming, which can be anywhere between hours to days. And this particular failure eventually lasted days. As you might have guessed, this is a true story in Azure. The root cause of this disaster is a firmware bug. The symptom is that the link silently drops packets without any signal. This is one instance of a broad category of failures, which are summarized by our colleague in Microsoft as gray failures. Gray failures is defined as differential observability, meaning that some part of the system, like the switches, might not notice a problem, even if other parts of the system, like the customer servers, are negatively affected by them. From our experience, gray failures contribute to a lot of the major availability breakdowns, as well as the performance anomalies in cloud environment. So detecting such gray failures is crucial to maintain a highly available data center. In order to detect the network gray failure, we've designed a system called NetBouncer. Of course, you may wonder why yet another monitoring/failure localization system. Indeed, there are many of them. I only list some here. I promise you I will circle back to this later in my talk. But for now, it is a combination of the following 4 requirements which motivate NetBouncer. First, in order to detect gray failure, the monitoring system should detect failure from an end host perspective. Second, the monitoring system needs to be transparent to current software stack. This is crucial in production, because if your system requires to modify the core part of the existing system due to concern about adding too much complexity to the maintenance or negatively affecting the software stability, your system might not even get a chance to be deployed. Third, in order to be useful in production, your system should pinpoint the failure in the granularity of a link or switch instead of a network region. Last but not least, your system should have very few false positives. This is important to give our network operator a solid confidence on the system. So now NetBouncer is such a system. NetBouncer is running 24/7 as a troubleshooting service in Azure. It is an active probing system which infers failures from path probing data. By active probing, I mean that the server will actively send in probing packets into the network and collect the number of packets sent and number of packets received to detect failures. As to the problem, which path to probe, there is a central controller which takes the network topology as input and output these probing plans, which contains for each of the server which path this server should probe. And finally, there will be a processor, takes this path probing data as input, runs an algorithm to pinpoint the link and device failures. This is a very high-level workflow of NetBouncer, which leads to the rest of my talk. First, I will introduce how to achieve an explicit yet efficient probing. Then, I will talk about which path to probe. Finally, about how to infer failures from path probing data. Due to time limit, this part will be brief. Now come to the first part. In order to cover the whole network, as well as to be aware which links a package goes through, NetBouncer requires a server to explicitly probe a path with low cost. By explicit, I mean that a server can decide ahead of time which links a package will path. Since traditional probing methods like ping or traceroute don't fulfill our requirements, NetBouncer uses a technique called IP-in-IP to achieve this path probing. This IP-in-IP forwarding logic is implemented within hardware, so it is efficient without involving any switch CPU cycles. On top of this IP-in-IP, NetBouncer uses a probing strategy called packet bouncing. It means that a server will ask a switch to bounce back the packet, like in this example in the graph. The packet bouncing provides us a simpler model because every link will be evaluated bidirectional so that we can have an undirected graph as our model. And it also simplifies the fault tolerance because the sender and the receiver don't have to synchronize the packet status because they're the same server in our case. Next, let's consider the second problem, which path should be probed. Before diving into the detail of this question, let me first model the whole problem. We abstract the data center network as an undirected graph where the vertices are the devices and edges are the physical links. For one probing path, where a server sent 100 packets and got 49 back, we say that the success probability of this particular link is 49%. These path success probabilities are what we could observe, but instead, the link success probability are what we want to know. In this example, there are many explanations. In order to tell which one of them is choose, we can probe another path indicated by this orange dashed line, which differs only on the first link from our original blue lines. If the orange line is totally healthy, then we know that case 1 should be the fact. I bet you got the flavor here. Based on the different path probing observations, we can infer the link success probability. And we will report those whose success probability is lower than a certain threshold, for example, 99%. In order to figure out all the link success probability, a natural question follows is that which path should be probed so that all the link success probabilities can be uniquely determined. In a production environment, this is not necessarily an easy question to answer due to two real-world constraints. First, in a large data center, inevitably, there are switches fail to respond to our probing, mostly because they are low-end or legacy switches which does not support IP-in-IP. Second is that the sender and receiver have to be the same server, which is NetBouncer's design choice. With these two constraints, we found that sometimes it is impossible to uniquely identify all the cases. Let me show you why using an example. Suppose we want to infer these 4 links from x1 to x4, but unfortunately, the shaded switch cannot be bounced. In this case, all the relevant paths will be this y1, y2, y3, and y4. Intuitively, we found that we have four equations and 4 variables, but intuitively we found that one equation is redundant because y1 times y4 equals y2 times y3. More formally, if we take logs on the equations, we have these 4 linear equations, which is not full ranked. In our context, this means that there are infinite combination of x1 to x4s, which are consistent with our observation, y1 to y4, which further means that the reported faulty links can be arbitrary. The good news is that in order to find when it is possible and when it is not, we come up with a theorem called the sufficient probing theorem. Details are in your paper. This theorem provides us a simple probing plan. That is, for each of the server, just probe all the top layer switches. And this probing plan gives us a necessary and sufficient condition for having a unique solution for link success probability. This condition is that for each node in the graph, as far as there is one good path through this node, then there will be a unique, we can uniquely identify all the success probability of all the links. Let me show you an example. For example, let's see this shady node in the graph. No matter how many lossy paths through this node, as far as there is one good path through it, then we can uniquely identify all the link success probabilities. The intuition of the theorem is that a good path implies that all the links within this path should also be good. By applying this condition on the whole network, we can split the graph into two. A subgraph with each of the nodes has at least one good path and an unsolvable part. If we examine the unsolvable part, we found that these are a set of devices that not even one good path through them. Usually, we have hundreds to thousands of paths through one node. If not even one of them is good, it's pretty strong a signal that this device itself has some problem. And this is our device failure detection algorithm. Finally, the last missing piece is that how can we pinpoint the faulty links in this subgraph with unique solution? But due to time limit, I will only deliver the overall problem and one real challenges as well as our solution. So the problem is that given the path probing data, YJs, how can we infer the link success probability xi's such that fit our observation the best? This is a classic optimization problem as follows. In this equation, the YJs, again, are what we could observe, and xi's are what we estimate or guess. However, simply solving this problem produces many misreportings, especially false positives. Next, I will show you one reason as well as our solutions. In real-world workload, there are data inconsistencies which lead to false positives. Here is a simplified example. Suppose we have this link which drops half of its packets. So if we probe the path through this link, we would expect to see 50% of the packet jobs. However, sometimes we may find that our measurement fluctuate. In this case, we only got 49 packets back. And the system might believe that this red link also dropped 2% of the packets, which is a false positive. Due to the ever-changing status and the limited number of probing packets, our measurement might not fully align with each other. In addition, the inference results may overfit our imperfect observations, which usually end up with false positives. To tackle this problem, we propose a specialized regularization term, which encodes our troubleshooting domain knowledge. And here is the plot of this regularization term. The lower the y-axis, the smaller the fitting error. The regularization term intends to pull the good link to be better and push the bad link to be worse. The intuition behind this is that the failures are rare, and the vast majority of the links are healthy. There are more challenges for failure inference algorithms. Please check our paper for details. Now, let's come to the evaluation part. There are 3 evaluation questions we want to answer. First, in production, what failures have been detected by NetBouncer, but not by our previous monitoring systems? Second, compare with previous inference algorithms, how accurate is NetBouncer's algorithm? Finally, is NetBouncer fast enough to handle hundreds of gigabytes of data per hour in production environment? Now let's come to the first question. I will show you one real example, and there are more in our paper. In 2015, we've observed that many of our customers experienced package jobs and latency increases. However, the traditional monitoring system says nothing. This is another NS problem. One significant difference here is that we have NetBouncer this time. By using NetBouncer, we can quickly pinpoint where the problem is. And here is a package job probability figure for the dropping link. The x-axis is the time. The y-axis is the package job probability, which is about 15% in this case. And usually, the link should drop less than 0.1% of the packet. The root cause of this grid failure is a bug in the line card of a spine switch. Because this is a spine switch, it affects a large region of the network. Without NetBouncer, it will be really tricky to find where the problem is. Next, let's compare the accuracy of NetBouncer's algorithm with previous ones. This is done by simulation where the ground truth is known. We simulate a standard 3-layer cloud network with 1% faulty links and 10 faulty devices. Please see our paper for other settings. We compare with 2 algorithms, Detector, which is the state-of-the-art heuristic algorithm, and Netscope, which also infer failures as solving an optimization problem. Here are the results. The blue bars are the number of false negatives, and the red bars are the number of false positives. The y-axis is in log scale. The last cluster is NetBouncer. We have 0 false positive and 0 false negative in this particular experiment. However, we cannot guarantee 0 false positive or negatives. And we do experience some in other experiments. Finally, let's see NetBouncer's algorithm's performance in real data. We choose 1-hour data from 2016, which is about 130 gigabytes in size. This figure depicts the time NetBouncer spent on detecting failures for every 5 minutes. We can see that in all cases, NetBouncer can finish within 60 seconds or 1 minute. This is fast enough for us for now, and we believe there's a huge opportunity for optimization. And finally, here are the most relevant works to NetBouncer. NetBouncer fall into the category of network tomography, and we focus on the data center network or cloud network to be specific. Some of the previous work focused on different setups. For example, Netscope, they target internet where the network topology is unknown and you can get little help from routers. Because NetBouncer is specifically designed for data center network and we consider the real world challenges, so it outperforms previous works in data center environment. There are many other network troubleshooting systems or systems can be used for troubleshooting. They are complementary to NetBouncer. For example, Panorama is a system that can detect software grade failures, which is complementary to NetBouncer, which target the network grade failures. Other systems like Trumpet provide many more functionalities than just the localizing failures, but it requires modifying the hypervisor. NetBouncer use IP in IP for path probing. Other source routing protocols might also be plausible. And previous probing plan design mostly focused on minimizing number of paths to be probed, which is not NetBouncer's goal. To conclude, NetBouncer provides a complete framework for data center network failure localization and has been deployed in Azure for 3 years and performed well. With this, I'd like to take any questions.
Hi, thank you for your talk. Cristina Anita Rotaru, Northeastern University. I was surprised in your evaluation to see that you didn't talk at all about overhead. So can you comment about that a little bit?
Yeah, very good question. Give me a second. Yeah, basically, NetBouncer had negligible overhead, but mostly because we send thousands of packets per path every 5 minutes. You consider that we have 40 gigabyte links throughput recently, so it's negligible. Yeah.
Thank you. And the comment about related work, and I didn't read your paper, so maybe you talked about it, but there is a lot of work in wireless, particularly wireless mesh, because you're looking at structures here that they're not necessarily, you're not looking just at one path, you're looking at trees or meshes from my understanding. I don't know if you looked at it, but you might want to look at it. There is also work in doing this type of fault detection in more complex network structures when you have also adversarial environments. And so anyway, just wanted to mention that.
Yeah, so definitely those works inspire us, and we own depth to those works. But yeah, so I totally agree with you in that case. But like we have different challenges. Let me elaborate a little bit more. So basically, data center environment, as you said, we don't have adversarial nodes in that sense, but also we actually have to tackle at least two major differences. One is the volume is really like hundreds of gigabytes per hour. We pay like some attention on how to choose a algorithm which can finish within our tight time budget. That's one thing. Another thing is I think we are targeting not only detecting like 10% packet loss, we're targeting 1% or even less packet loss. So that's a significant difference. But I totally agree with you.
Thank you. Thank you.
Thank you.
Let's take another question.
Hi, very nice talk. So my question is that does the topology asymmetry matters much for your problem? And it doesn't matter. It doesn't mean that the topology is not a closed network.
So you're asking will our NetBouncer work for other topology?
No. I mean that I believe that there is some sense of asymmetry in the closed network, right? So asymmetry.
So wait, are you saying is there asymmetry in that class network? Is that your question?
Yeah.
Okay, so for NetBouncer we present here. So for the theory part, we do not assume that, but in reality, in Azure we do have that. So basically, we have a theorem that is based on the cloud network. We prove it is based on the cloud network. It's more or less in a theoretical regime where we have to have that. But without that, in actual use in Azure, we do have asymmetric topology. Yeah.
Okay, so.
Why don't you?
Thank you.
So we're at time, so maybe you can all ask Cheng more questions while we're outside. Cool. Let's thank the speaker again, and this is the end of the session.